Okay, so we left off on the last part. I'm struggling to describe this ancestor. Hey, you look at it and it looks like somebody ran over a, I don't know what, just flattened out, squished out tetrapod amphibian ancestor. But based on the fossil evidence and what evidence we have today, this is what the tetrapod, four-legged ancestor looked like. Fish evolved and diversified into all sorts of different groups. Some of the fish evolved towards this amphibian. Now, we have fish today, and I'll show you some of this later on, but we have fish today that have legs. They walk. They walk on the bottom of the water. Some actually get out of the water and walk. So thinking that a line of fish over hundreds of millions of years could evolve into something like this amphibian is not out of reach. It's well within reach, well within possibility, and all the evidence points to that is how this amphibian ancestor with four legs came to be. Again, from the amphibians, we see giving rise to reptiles. Not a huge stretch to go from a salamander to a lizard. Change the skin, change some bone structure, adapt to life on land a little bit better. And then the reptiles, major evolution. Phenomenal group, gave rise to all sorts of diversity. Birds, dinosaurs, mammals, etc. All right, so when we look at this goofy, weird ancestor, you come up with whatever term or name or analogy you can. Officially, I want to give you the scientific name. This officially, and when we're doing the scientific name, we italicize. There it is, it's italicized. I'm going to write it out. All right. Tiktaalik rosea is the official scientific name of this ancestral amphibian. This guy had gills / rudimentary lungs. So it's not a true gill, not a true lung, kind of this in-between weird thing. It had wrist bones that enabled it to flex its, let's call it, wrists and hands. And it's kind of an in-between. It's this weird, oh, that shouldn't be italicized, this weird intermediate between fish and amphibians. So then this group continues to evolve and change and give rise to the amphibians. All right, now from the amphibians, as I mentioned earlier, we get all sorts of diversity that leads to birds, dinosaurs, lots of other reptiles, and eventually the mammal line. All right, so this is about 380-ish million years ago. People call this thing the Tiktaalik. Some people are calling it the fishapod because it's kind of an in-between, a half and half. Remember planimal? Well, here's a fishapod. Not an amphibian, not a fish, an in-between. So this body plan evolves to have four limbs. And this continued to give rise to all sorts of diversity. So consider the skeletal structure of a human. Here's ours. If you take a look at the bones, very similar to the bones that we see in amphibians and reptiles and birds. So bone, there should be bone plan. All right, so all these groups have a very similar bone plan. Proportions are different, absolutely. That doesn't look like a bird skeleton. But you think about the general bird structure. Think about the general reptile structure. Four limbs, backbone, rib cage, skull, hip bones, shoulders. There's a similar pattern that we're seeing here when we look at and compare these skeletons. So what we call this in evolution are homologous structures. So here's a better example of what I was describing in the previous slide. So let me get this up here. Term to know. All right. All right. So the reason we have a similar bone plan, so here's the arm, or called the forelimb of a bird. You have a humerus, you have a radius and an ulna, and then you have the metacarpals and the phalanges. Here's ours. Humerus, that's your big upper arm bone. Radius and ulna, forearms. The metacarpals, wrist bones. Phalanges, your finger bones. Look at all four examples here. Bird, mammal, reptile, amphibian. Same pattern. Yes, proportions are different. No disagreement there at all. But the same bone pattern. We go back, we see that bone pattern. Okay, so it's showing common ancestry, showing relatedness. Humans didn't poof magically just have this brand new arm structure show up in a human. It's because we have a common ancestor to all these other groups. Why else does a lizard have the same bone pattern, and the frog have the same bone pattern, and the bird have the same bone pattern? This is due to evolution. This is due to natural selection. Okay, so common ancestry, right? All right, so let's get even more specific. Here's humans. We're mammals. What about the rest of the mammals? What else do we see in the rest of the mammals out there? Well, let's drill all the way down to primates. Forget cats and dogs, forget horses, forget deer, forget rabbits, bats. Let's go primates. Primates. Look at the hand on a primate. What makes our hand different than the hand of or paw of your cat or your dog or the bat or the whale, the dolphin? Same bones, but the primate twist, tweak, uniqueness. What makes all primates different is the fact that, and you're probably using it right now, the thumb is opposable. Take your thumb, it can cross over your palm. I can't do that on my dog. You can't do it on a cat, a horse, it doesn't work, a bat. No other mammal can do this. This is the primate feature. So why do all primates have this? Because all primates have a common ancestor. So whether you're talking about this little goofy guy called a tarsier, a gorilla, or a human, we all can cross our thumb over our palm, grasping hand, opposable thumb, because our ancestor had this. And then the ancestral primate gave rise to all the different groups of primates out there. So again, common ancestry, natural selection. Primates evolved to life in the trees. The earliest primates were completely tree dwellers, run around at night, And then as the environment changed, they started adapting to different environments, got bigger, became terrestrial, started walking on two legs versus four, etc. That's all part of primate evolution. But the primates, the original ancestral primate, started out with his hand. So that little tarsier, this little guy here, is the closest living relative to our primate ancestor. They resemble him the most. So this keeps showing relatedness, common ancestry. Now, if we drill down even further, getting closer and closer to human beings, where did human beings, Homo sapiens, come into the picture? And we can look at just our branch of the evolutionary tree and say, okay, what makes us different and unique? And where did our ancestral trait come from? Well, we can go back about 4.5 million years to a hominid ancestor. This is not a human being. All right, this is not a modern Homo sapien. We'd call it a hominid. Okay, so what made hominids different than the apes, than the chimpanzees, than the spider monkeys is we evolved to become bipedal. We're walking upright on two legs because none of your other primates do that. They're not built to be two-legged. They don't walk on two, they walk on four. And then the other thing that made us a little different is our unique hand structure, our bone pattern. This is a hand, reconstructed hand of Ardipithecus ramidus. This is an ancient hominin that goes back about 4.5 million years ago. Put your hand down next to it, pretty much identical. It hasn't changed much. It evolved in our early ancestors. It worked, it's functional, it does a great job, it enables us to live the lifestyle we have, and it's been working for over 4.5 million years. All right, so again, as we keep looking at relatedness, we keep seeing more and more and more examples of how all animals are related. So, all right, so a lot of those examples were just based on physical characteristics. This trait, that trait, what we can see, fossils, skeletons, bones, etc. Now let's talk about the genetics. Let's look at the molecular side. How do we know we're related to animals? Well, let's look at the DNA. Our genetics. So we have a molecular relatedness to other animals. And one example here is, this is a fun, some fun information that was discovered fairly recently. Let me move down one. It's a thing called the sonic, the sonic hedgehog gene, or SHH for abbreviation. So yeah, like the little character, Sonic the Hedgehog, the SHH gene. And what this gene does is it regulates the development of limbs, the limb growth. It basically controls how your legs and arms are going to grow. And what we see this is applied across amphibians, reptiles, and birds are considered reptiles. So I'm not adding birds here, but they're grouped under the reptiles, and mammals. So same gene, all three groups, because of common ancestry. That is the gene that dictates how the limbs develop and grow in these animals. So how cool is that? For here's another line of evidence showing relatedness across all animals. All right, so we'll talk more about this gene, the sonic hedgehog gene, in the next part of the lecture.